requested that we talk about the mutual induction. So I'll quickly go through these 3 questions. Number 5, the figure below shows ends of a solenoid connected to a galvanometer as shown below. A magnet is plunged into the coil. That means the magnet is coming in. Show the direction of induced current. So you need to find out from Lenz's law. The Lenz's law states that the direction of induced EMF is such that the induced current which it causes to flow creates a magnetic effect here on the solenoid. It creates a magnetic effect which opposes the change causing it. What change is causing that current to flow? It is the movement of this magnet. So a pole will be created here to oppose the movement of this magnet. So as the magnet comes in, a north will be created here to oppose the magnet from coming in. So since this is north, the other side will be south. Then using the right-hand grip rule, we are able to determine the direction of motion of the current that is induced in the coil. So the arrows, of course, if this is north, then the thumb should point to the right. The arrows point downwards on this conductor here. Number 6, a coil X is moved quickly away from the end of a stationary magnet Y, and current flows as shown in the figure. So we can see the current is flowing using the right-hand grip rule. It means this side will be north, this side will be south. Therefore, if this is north, this is south, then this south is opposing this magnet, because from Lenz's law, the pole that develops here opposes the incoming magnet. So this will be south also, so that it's opposed through repulsion, and then Y is north. So the polarity of Y will be north. Number 7, we have mutual induction, 2 coils. This is a primary, this is coil P, this is secondary, coil Q. When the switch K is closed, an EMF is induced in coil Q, this one. Similarly, an EMF is induced in coil Q when the switch K is opened. Explain. So as I said on Wednesday, in your explanation, you must state the rate of change of magnetic flux linkage linking the primary and secondary. So you say when the switch is closed, current flows in the primary, coil P. A magnetic flux changes from 0 to maximum, or a magnetic flux linking P and Q changes from 0 to maximum. It builds up. This causes an EMF to be induced in Q. Then on the other hand, when the switch is opened, current drops from maximum to 0, causing a change in the magnetic flux linking P and Q. Hence, a current is induced. So we will see a deflection in this galvanometer. But during opening, it deflects in the opposite side as during opening. Now, you can also be asked, suppose this is A, this is B, this is C, this is D, then you're asked to label the polarities. So we know that when you close the switch, this one becomes a north, this becomes a south. North to the left, south to the right. A pole develops here that opposes this south, and that pole will be south. So this will be south, this will be north when the switch is closed. That is north, south, south, north. When we open the switch, then remember the south that was here will be disappearing because the magnetic flux changes from maximum to 0. So that south is going away. So a north will develop here to oppose this south from going away. So when you open the switch, this remains north, south, north, south. That is during the opening of the switch. To explain why the induced current in Q is higher when the switch K in P is opened than when it is closed. When the switch is opened, current takes a shorter time to die off from maximum to 0 than to build up. Current takes a shorter time to die off than to build up, hence a higher rate of change of magnetic flux linking P and Q. That's why in an induction coil, we prefer using current dying off so that a larger EMF can be induced. Yes, Andrew?
So please, can you pardon?
Which part?
This last part.
The first one?
No.
The second?
Yeah, Roman 2.
Okay, Roman 2 have said that we are being asked, explain why the induced current is higher during opening of the switch than during closing of the switch. And I've said that during opening of the switch, current takes a shorter time to die off than to build up. And one of the factors affecting the magnitude of induced EMF is rate of change of magnetic flux that links the two coils. So rate of change means speed at which current is changing. So when you open the switch here, current dies off very quickly than when we switch on. Even in nature, naturally, it's very easy to destroy something, and it's very hard to build it up. Even when you enter a room and you switch on the lights, some bulbs, you will see some bulbs struggling to switch on, but you will never see a bulb struggling to go off. So current takes a shorter time to build up than, no, current takes a shorter time to die off than to build up. Hence, a faster rate of change of magnetic flux linking P and Q. That's the answer to Roman 2. Roman 3, with the help of diagrams, show the direction of the induced current in Q when the switch is closed and when it is opened. So as I said, you need to know that if this is north, this is south. When we switch on the switch, this is north, south. So a south creates here. A south develops here due to based on Lenz's law. This will be a south. Therefore, using the right-hand grip rule, if this is south and this is north, then the arrows will point down on this coil, downwards. Then this way, through the galvanometer, then back. When we switch off, this remains a north, this remains a south, but then a north develops here. That's why the direction of the the galvanometer will be opposite. So this remains a south, this becomes a north, and based on the Lenz law, right-hand grip rule, the arrows on this conductor will be upwards. They face up. So that's the answer to Roman 3. Roman 4, which phenomenon is being demonstrated in this setup? This is mutual induction. Roman 5, suggest a way in which the induced EMF in the secondary coil Q can be increased. So here, for us to increase the magnitude of induced EMF, we can increase the number of turns of this coil Q. Increase the number of turns of the coil Q. Secondly, we can also increase the primary current here. We can add some cells. Don't say increase number of cells. You say increase the amount of current in coil P. So I think I've explained mutual induction, though that is not what we've planned to do today. So allow me to share today's work. It's a past paper, which is it's Mokasa. Unless there is a question on mutual induction. Yes, Jose.
My question was,
Yes.
according to the diagram,
Yes.
the direction at which the current is flowing,
yes,
is when the switch is open. And
no,
according to your answer, you are saying that when the switch is closed, it will remain the same. So I was confused there.
Yes. Have we changed the poles? We haven't. This remains positive. The left is positive, right is negative. So
No,
this direction, the direction drawn here, does not change whether we are switching on or switching off.
Oh.
It remains the same. What changes is the secondary coil here. So,
okay, sir.
Yeah, the current will change here when during switching off, because it's relying on the behavior of the pole that is here, which is a south. Is it being created or it's dying off? If it's being created, then a south builds here opposing it. If it's going away by switching off, then a north creates here opposing it. Opposing it's going away. Umeelewa?
Yes.
Yes. So direction in the primary doesn't change. So let me open this Mokasa paper 1. So I hope we can see the paper 1 on the screen. We start with the section A. It is believed that the sun goes around the earth in a circular orbit continuously. State the branch of physics that studies this. this is mechanics. Mechanics is a study of motion of objects under the influence of force. Study of objects under the influence of force. The sun is actually the earth that goes around the sun under the influence of the gravitational constant force. Number 2, figure 1 shows a micrometer screw gauge being used to measure a diameter of a ball bearing. Preston, question? Yes, Preston.
Sir, could you kindly pardon the answer to number 1?
The answer is mechanics.
Thank you.
Yeah. I was just going further by explaining what mechanics is, and it's a study of motion of objects under the influence of force. Just in case next time you're asked, define mechanics. So, number 2, if the instrument has a negative zero error of 0.01, record the actual diameter of the ball bearing. So, the main scale reading is 3.5. I think we can also see 3.5. Then the thimble scale reading is the 4th division, total 3.54. Then add error. If we add 0.01, we get 3.55. 3.55 is the answer to number 2. Yes, there's somebody who has a question. I think he has disappeared. You can ask later. Number 3, what is surface tension? We are being asked to define surface tension. Surface tension is basically the force acting on the surface of a liquid. Force acting on the surface of a liquid that makes it behave like a stretched elastic skin. Force acting on the surface of a liquid that makes it behave like a stretched elastic skin. Part B, figure 2 shows a funnel dipped into a liquid soap solution. We can see the funnel over there. Explain what happens to the soap bubble when the funnel is removed. So, we are told to explain 1 mark. The bubble moves up. The bubble moves up to a flattened film. It will come to this neck over here. The bubble moves up to the flattened film so as to occupy the smallest area possible. It moves up to a flattened film so as to occupy the smallest area possible. I think we all know that surface tension tends to occupy the smallest area possible. Number 4, 2 identical well-lagged cans, A and B, each has a volume of water and are fitted with thermometers, TA and TB, as shown in the figure below. You can see this is A, this is B, TA, TB. Water in A is at 45 degrees Celsius, while water at B is at room temperature. I think they've been interchanged. Water in A is at 45. We can see A has 25 and B has 45. This is hot water, cold water. So let's use the diagram, the diagrammatic labeling. This is 25, this is 45. This has an error. Cold water is poured carefully in A and simultaneously an equal mass of hot water poured in B. State which of the thermometers record a lower reading after a short while. I think here the answer is B. And the explanation is cold water in A easily gain heat by convection. Cold water in A easily gain heat by convection, unlike B, cold water is denser, hence sinks to the bottom of the container. I hope we have understood that explanation. Yes, Meshak?
Excuse me, Jack, can you repeat the answer of A? The answer for A.
For A.
Yeah.
Thermometer B. Then
Yeah.
explanation, cold water in A easily gain heat by convection, unlike in B, where cold water is denser, hence sinks to the bottom. Give a reason. The reason is hot water is less dense than cold water. Hence, convection current takes place in hot water. Hot water is less dense than cold water. Hence, convection takes place in hot water. Here, the language used is comparative. Make sure you use comparative language, denser, less dense, and so on. Number 5, we have a system uniform bar of length 1.4 meters pivoted near one end. The bar is kept in equilibrium by a string as shown. I think the bar is a bit skewed, but we follow what we're being told. The bar is kept in equilibrium. But when you look at it, it may not be flat, but it's in equilibrium. Given that the weight of the bar is 1.5 newtons, determine the tension in the string. Now, tension in the string, you first of all start by saying F1 D1 equals to F2 D2. The weight of this bar is in the middle here. And we are told that it's 1.5. So somewhere here you draw a weight downwards and label it as 1.5 newtons. That is our clockwise force. Our anti-clockwise force is the tension in this string. So we take 1.5 multiplied by distance to the pivot, from the center to the pivot here. The length is 1.4 meters. So halfway is 70 centimeters. So from 70 to 30 here, this arrow should be here. So distance to the pivot will be 40 centimeters. So 1.5 newtons times 0.4 meters to the pivot, this distance here, equals to tension times distance from this string to the pivot will be 90, I think 90 centimeters, because from here to here is 30, from here to here is 20, that's a total of 50. 140 centimeters minus 50 gives us 90 centimeters. So from here to here is 90 centimeters. So this is the equation. 1.5 times 0.4 equals to T times 0.9. 1.5 times 0.4 equals to T times 0.9. And our tension will be equal to 0.6667 newtons. 0.6667 newtons. Question 6. Below is a solid frustrum of a cone resting on its narrow end of a horizontal flat surface. The solid is made of a uniform material. Name the state of equilibrium of the solid on the surface. So this is a stable equilibrium. Stable equilibrium. If you're asked to explain, you say, when a small force is applied on the object or on the solid, it returns back to its original position. It does not topple. Locate the center of gravity of the cone and mark it M. So you draw the diagonals. You will use a ruler, draw a diagonal from this corner to this corner, and another one from this corner to this corner. And you find that our M is somewhere down here. So the position of the center of gravity is down there. Number 7, some pollen grains were placed in water to study Brownian motion in liquids. State and explain the nature of the observed motion. So of course we see, state and explain means you give two answers. So you see pollen grains are seen moving in continuous random motion. That's the first mark. Pollen grains are seen moving in continuous motion. The second mark, this is due to uneven bombardment by invisible water molecules. Uneven bombardment by invisible water molecules, which are in constant random motion. So this is the main mistake that many students make. Somebody says this is due to uneven bombardment by invisible water particles or molecules and stops there. That is an incomplete answer, because you have not told us that those molecules are in constant random motion. So make sure you complete the statement by saying this is due to an uneven bombardment by invisible water molecules, which are in constant random motion. Question 8. When estimating the diameter of an oil molecule, a student measured the diameter of an oil drop using vernier calipers. State the assumption she made in this experiment. Assumption. So the assumption is the oil drop is a perfect sphere. The oil drop is a perfect sphere. The other two assumptions do not apply, because when you say that the oil patch is a perfect circle, yet this student has done nothing about the oil patch. It's about the oil drop. Or somebody else say the oil patch is 1 molecule thick. It's also wrong, because we are not measuring the oil patch radius. We are measuring the diameter of the oil molecule. Number 9. A Form 1 student at Upper Hill Secondary School had a tin can half filled with water as shown. She heated the water and let it to boil for some time. The open top was then sealed and cold water poured on the can. The can was observed to crash in. State why. A, the water was let to boil for some time. The reason for boiling the water is to expel air from the can. To expel air from the can, of course, steam will be produced. Then that steam expels air. B, explain why the tin can crashed. So you say, this is 2 marks. So the first mark you say, a partial vacuum is created after air is expelled. That's the first mark. A partial vacuum is created after air is expelled. The second mark, you say, on pouring cold water, pressure inside reduces. On pouring cold water, pressure inside reduces. Then higher atmospheric pressure on the outside forces the can to crash in. Higher atmospheric pressure outside the can forces it to crash in. Remember, I'm using the word higher atmospheric pressure. That's comparative language. You can use greater atmospheric pressure. And we have also used the pressure inside reduces. That is a comparative language. Initially, it was higher. Therefore, it reduces to a new pressure. Number 10, the temperature of a gas in a container of fixed volume was gradually lowered and the corresponding pressure measured. Below is a sketch graph showing the variation of pressure with temperature from the experiment. So we have a graph here. The temperature is in degrees Celsius. Define temperature X using kinetic theory of matter. Remember, X is called absolute zero temperature. And we have so many definitions of absolute zero temperature. One of them being that this is the temperature of a gas whose volume is assumed to be 0. But now that volume being 0 is not kinetic theory of matter. So we say this is the temperature at which the kinetic energy of the gas particles is assumed to be 0. Temperature at which the kinetic energy of gas particles is assumed to be 0. So when you are directed to use kinetic theory of matter, mention the kinetic energy of those gas particles. Part B, State the reason why temperature X cannot be achieved. The reason why we can't achieve this is because the gas liquefies before attaining absolute zero temperature. The gas liquefy before attaining absolute zero temperature. It changes to a liquid before that temperature. Yes, we have somebody who was raising his hand. He has also disappeared. Feel free to ask any question. Number 11. A steel wire of length 20 centimeters was coiled several times, make a spring. The spring was loaded with various weights and a graph of force against extension plotted as indicated below. So, in figure 1, indicated in figure 1 below. So this is the original graph that was drawn. State any two changes that could be made on the spring to obtain the graph in figure 2. So you ask yourself, have we increased the spring constant or we have decreased it? The answer is we have reduced the spring constant. Because when you calculate the slope here, is higher than the slope here. So K has decreased. In other words, the question is asking, give two changes that you can do on a spring to reduce its spring constant. So one of them is increase the number of turns per unit length of the spring. Increase the number of turns per unit length of the spring. Yes.
Could you repeat the previous, the last question that you've done, the previous one, the last answer?
That's number 10.
Yeah.
Both A
The
and B.
Yeah.
B.
Yeah.
Okay. So number 10, A, I said that when we define X using kinetic theory of matter, then we have to talk about the kinetic energy of those molecules. And we said that this is the temperature of the gas at which the kinetic energy of the gas molecules is assumed to be 0. That is for part A, temperature of the gas molecules, temperature at which the kinetic energy of gas molecules is assumed to be 0. B, reason why X cannot be achieved. Remember, this is negative 273 degrees Celsius. By the time you reach there, the gas will have changed to liquid. So the answer is the gas liquefies before attaining the absolute 0 temperature. The gas liquefies before attaining the absolute 0 temperature. We are on number 11, and the question is basically asking, state two ways in which you can reduce the spring constant of a spring. Spring constant is the strength of a spring. The higher it is, the stronger it is. When K is low, then the spring is also weak. So one of the things we can do is we increase the number of turns per unit length. Don't just say increase number of turns, because sometimes you can increase number of turns and you make it even stronger. So it should be increased number of turns per unit length. Then 2, you increase the diameter of the spring. Increase the diameter of the spring, or you make it wider. Number 12, an object is fired vertically upwards from the ground level with a velocity of 50 meters per second and reaches a maximum height h. It falls back to the ground and bounces to a height of 4 meters. Sketch a velocity time graph to represent the motion of the object from the time it is fired till it bounces to the height of 4 meters. So here you must know that when we fire this object, it's going to attain a certain height, which is higher than this one, this 4 meters. Reason being, when it falls back to the ground and bounces, some of the energy is converted to heat and sound, and even deformation of the ground. So it will not have all the energy to bounce back where it was. So your line should start from here, because we are firing it somewhere up here. We fire it with a certain initial velocity, which is very high. It rises up, so your line drops to a certain level here. At that point, it has reached maximum height. It starts coming back, so velocity changes direction, so negative side. So you continue with the line, straight line, reaches somewhere here, a level that was not where you started from. If this was probably 20, down here could be 10 or even less than 10, but don't put values. Then after that, you return the line up to 0. So straight line from up here, straight line, up to a certain level, then back to 0. Yes, Andrew.
Yes, since you have been told that it bounces back, why are you moving in the opposite direction?
No, I'm saying, remember we have 3 directions here. We are starting from here, okay? It goes up, reaches somewhere and stops. Iko juu sasa hiyo, iko maximum height reached. Then it starts coming back. It means it changes direction. So negative side, we continue with the line. This is coming back. When it comes back, it strikes the ground, then it bounces off, changes direction again, back to 0. So your line will come this way and then rises to 0. Sawa. Don't know if you still have something to say, Andrew.
It's okay.
Umeelewa?
Yeah.
Okay. Any question in section A? We move to section B. Section B, 13A, state Bernoulli's principle. Bernoulli's principle states, if the fluid is incompressible, non-viscous, and its flow is streamlined, an increase in velocity leads to a corresponding decrease in pressure. If the fluid is incompressible, non-viscous, and its flow is streamlined, an increase in velocity leads to a corresponding decrease in pressure. So remember to mention all the three conditions. It must be incompressible, it must be non-viscous, and it should flow in a streamlined manner. Yes, Brian? Yes.
I wanted to ask, is there a difference between Bernoulli's principle and Bernoulli's effect?
Yes, I know KLB states the principle using the equation that says the sum of potential energy per unit volume and kinetic energy per unit volume and pressure is a constant. That is Bernoulli's equation. But the principle is what I've said here. This, what we have said in KLB is written as Bernoulli's effect, but it is the principle. So when you are asked to state it, say the way I've given it here. Just like other areas, like when we calculate work done, you find that KLB has treated the negative side to be like a vector. You minus the work done, yet we don't have negative work done. So the same mistake has been done when it comes to Bernoulli's principle. So you say if the fluid is incompressible, non-viscous, and the flow is streamlined, an increase in velocity leads to corresponding decrease in pressure. That is the principle. Part B, in deriving the equation of continuity, it is assumed that the fluid is non-viscous. Explain the effect of increase in fluid viscosity on the type of flow. So when we increase the viscosity, then we increase the viscous drag. So the answer is increase in viscous drag changes the direction of particles. Hence, the flow becomes turbulent. Increase in viscous drag changes the direction of motion of particles. Hence, the flow becomes turbulent. So if it's a turbulent flow, then the equation does not apply. The equation A1 V1 equals to A2 V2, or AV equals to a constant. That is the equation of continuity. AV equals to a constant. The flow must be streamlined, not turbulent. But see, the figure below shows water in a horizontal tube of two different sections, AB and BC. So we can see AB and BC. We are given cross-sectional areas. The cross-sectional area piston on the piston is 1.5 square centimeters, while that of section BC is 2.0 square millimeters. If the piston moves 12 centimeters from A to B in 3 seconds, calculate 1, the volume flux of water. We all know that volume flux is cross-sectional area multiplied by velocity. Cross-sectional area is 1.5. We change to meters squared. That will be what? When we convert to meters squared, we will have 1.5 multiplied by 10 to the power negative 6. . . not 6, but 4. 1.5 times 10 to the power negative 4 meters squared, multiply by, we are told that the velocity is 12 centimeters for every 3 seconds. So 0.12 meters divided by 3. So that's the same as 1.5 times 10 to the power negative 4 times 0.04. 0.04, and we get the answer to be 6. That is 6 centimeters cubic per second is the same as what? We multiply and see. Six times 10 to the power negative 6. 6 times 10, 6.0 times 10 to the power negative 6 meters cubic per second. 6.0 times 10 to the power negative 6 meters cubic per second, which is the same as 6 centimeters cubic per second. Yes, apps.
Please kindly repeat.
Okay, we start with the formula. Volume flux equals to AV, or area times velocity. So flux equals to AV. Our A is this area here, 1.5. So I said that we use SI unit, which is meters squared, sorry. So converting 1.5 centimeters squared to meters squared, we divide by 10,000. That's why I said it will be 1.5 times 10 to the power negative 4 meters squared. That's our A. Times velocity, we calculate it using these quantities given. We are told that water moves 12 centimeters from A to B in 3 seconds. So this is like 0.12 meters over 3. Displacement over time gives us velocity, which is 0.04 meters per second. So we will now have 1.5 times 10 to the power negative 4 times 0.04. And the answer is 6.0 times 10 to the power negative 6. 6.0 times 10 to the power negative 6 cubic meters per second. That is the volume flux. And remember, volume flux is the same as flow rate. Those two terms mean the same thing. Volume flux, flow rate is the same. This is the volume of a fluid that passes a point within 1 second. So the answer should be meters cubic per second. Before we look at the speed of water through BC, you can also be asked about mass flux. Mass flux is the mass of a fluid that passes a point in 1 second. And therefore we take volume flux multiplied by density. Because even in Form 1, mass equals to volume times density. So we take volume flux times density, or flow rate times density, gives us mass flux. SI unit of mass flux is kilograms per second. So 2 is asking, now what is the speed of water through section BC? So section BC, here the narrow section, we are given the cross-sectional area as 2.0 millimeters squared. So you will say A1V1 equals to A2V2. The flow rate in AB equals to flow rate in BC. A1V1 equals to A2V2. We already have A1V1 from Roman 1. So you will have 6.0 times 10 to the power negative 6 meters cubic per second equals to A2V2. Our A2 ndio hii imepewa 2.0. Change to meters times 10 to the power negative, because you now multiply, you ask yourself how many millimeters squared make 1 meter squared. We know 1000 millimeters equals to 1 meter. Therefore, 1 million millimeters squared equals to 1 meter squared. So we divide 2 by 10 raised to power 6, which is the same as 2 times 10 to power negative 6 times V2. We are looking for V2. This is the equation. 6.0 times 10 to power negative 6 equals to 2.0 times 10 to power negative 6 times V2. So V2 will be 3 meters per second. Velocity in the narrow section will be 3 meters per second. I hope everybody has understood that. Let's move to number 14. A COVID vaccine is only suitable when stored at a temperature of negative 440 degrees Celsius. A nurse has a choice of measuring the temperature of this vaccine using either mercury thermometer or an alcohol thermometer. Explain which of the two thermometers will be suitable. So the answer is alcohol thermometer. And since explanation is it has a lower freezing point. Mercury thermometer has a lower freezing point. Not mercury, but alcohol. Mercury freezes at negative 39. So you see by the time we reach negative 40, it's already a solid. Alcohol freezes at negative 115 degrees Celsius. So it will be able to measure that temperature. So the answer is alcohol thermometer, since it has a lower freezing point. Part B, below is a glass flask fitted with a tube and inverted in water. The temperature of the surrounding is slowly lowered. Slowly lowered. State the observation on the liquid level in the glass tube. Remember, the word is slowly lowered. We are not freezing it immediately using ice. So what we will see is water rises up the tube. Water rises up the tube. Explanation is air inside the glass flask loses heat, hence contracting faster than the rate at which glass contracts. Air inside the flask loses heat, contracting faster than the rate at which glass contracts. I'm explaining part 2, this one. So first mark is air loses heat, contracting faster than glass. Then second mark, this lowers the pressure within the flask. This lowers the pressure within the flask below the atmospheric pressure. Below the atmospheric pressure. So I hope that is clear. Remember, it's slowly lowered. If it's immediate, like we cover the flask with ice, then the observation will be different. Of course, what we will see is we may see bubbles. Bubbles may be formed because glass contracts fast, forcing some air out. Then after some time, air contracts faster than glass, hence water rising up the tube. But since the question says we are cooling slowly, then we only have one observation. Water rises up the tube since air contracts faster than glass. Then this causes a difference in pressure. Pressure difference between atmospheric pressure and air pressure forces water up the tube. Part C, you've been provided with the following apparatus. A glass bulb fitted with mercury, glass bulb filled with mercury fitted onto a hollow stem, ice, boiling water in a can, and a grid of equal squares. Use this apparatus to describe an experiment to make a graduated thermometer whose scale is in degrees Celsius. So this basically is testing you on how to determine the lower fixed point and upper fixed point of a thermometer. Then divide that scale into equal parts. So here we will start with finding the lower fixed point. So the first thing is we melt the ice. We heat the ice and allow it to start melting. Heat the ice and allow it to start melting. Because we know ice melts at 0 degrees Celsius. So the second stage is insert the bulb into the melting ice and mark the mercury level as the lower fixed point. You can use letter X. Mark the mercury level as the lower fixed point, X. The next stage now, we want to know the upper fixed point. And for us to determine the upper fixed point, we don't use boiling water. We use steam, because water can boil at even 95 degrees Celsius, which is a wrong value. So the next stage is suspend the thermometer above the boiling water under normal atmospheric pressure. Suspend the thermometer above the boiling water under normal atmospheric pressure. And mark the new mercury level as Y. Mark the new mercury level as Y. So y is the upper fixed point. And we are using what? Steam. We are not using boiling water. If you have to use boiling water, then you must ensure that this water is very pure. Number two, you are operating at sea level. Sea level means the normal pressure, 76. But since we may not get sea level, we will use steam. Then let's listen to GGT. You can speak. Yes. He has disappeared. Maybe you ask your question later. The next stage, now we have the lower fixed point X using melting ice and upper fixed point Y using steam. The next stage is now we subdivide. So the next point you say, use the grid to divide distance XY into 100 equal divisions. Use the grid to divide distance XY into 100 equal divisions. Then you conclude by saying that each division represents 1 degree Celsius. Each division represents 1 degree Celsius. Remember, this is a descriptive question. And it's, as you can see, 4 marks. So don't write 3 stages or 2 and expect 4. Make sure you write each stage, if possible, more than 4 points. Number 15. Define velocity ratio. If you have a question, ask. If you have a question, ask. Kipchumba.
Excuse me, Mwalimu. I wanted to ask, when are we likely to maybe end this lesson, because it's already 10:30 and we need to prepare for the next lesson.
We are finishing at 10:40. The next
Okay.
lesson starts at what time?
It usually starts at exactly 11.
11. Okay. Let's finish in the next 7 minutes. Sawa.
Okay.
We are finishing at 20 to 11. So we'll have enough time. So we can do number 15 quickly. We have someone else with a question. Yes.
Please send the paper.
Yes, I will share the paper with the form master. Then you can access it.
Okay.
So velocity ratio is the ratio of distance moved by effort to distance moved by load. B, the figure below shows a load of mass 20 kilograms being pulled up an inclined plane with a constant force of 150 newtons. The plane makes an angle of 32 degrees with the horizontal and the height of 3 meters. Determine the work done on the load. So work done on the load is the same as work output. Work output. So work output is we are raising 150 newtons multiplied by vertical distance 3 meters. That gives us what? 450. That is the load. No, the load is not. This is effort. The load is 20 kilograms. So we change 20 kilograms to newtons. That is 200 multiplied by distance moved by load is 3 meters. 200 times 3 gives us 600 joules. So that is work done on load. Then work done by effort is now the effort multiplied by distance moved by effort. So we first of all find distance moved by effort from here, bottom here to here, which is the hypotenuse. So using the sine rule, sine 32 equals to 3 over hypotenuse. So we get hypotenuse to be 5.661 meters. This distance here is 5.661 meters. Then we come and say that work done by effort is 150, because 150 is the effort, multiplied by 5.661. We get 849.2. That's the answer to Roman 2, 849.2 joules. Then efficiency is work output over work input multiplied by 100%. Efficiency, you can write it as a word equation. If you forget the symbols, just write as a word equation. Efficiency equals to work output over work input times 100%. So 600 over 849.2 times 100% gives us 70.65. 70.65. Let me respond to some questions, then proceed.
Excuse me, sir.
Yeah.
Can you quickly please go through the description question we did?
Description.
On the thermometer.
Okay,
thermometer.
I'm going. Let me repeat after these.
Okay.
Let me repeat after we have finished this, because some people want to prepare for the next lesson. Then the last part is work done against friction. This is the useless work done. Therefore, we take work input minus work output. Work input minus work output, which is 849.2 minus 600. That gives us 249. I think it's 248.8 joules. That is work done against friction. The difference between work input and work output. So we can stop there. We will continue from number 16. But let me go back to, based on your request, descriptive question. Those who want to prepare for the next lesson, you can leave as I go through this question again. We are given a glass bulb. Remember, this is a plain glass bulb filled with mercury. No markings on it. Fitted on a hollow stem. Ice, boiling water in a can, and a grid of equal squares. Use these apparatus to describe the experiment to make a graduated thermometer. So I said you start by identifying the lower fixed point. So for us to get the lower fixed point, which is always 0 degrees Celsius, we use ice. Melting ice, rather. Not just ice, because ice can exist at -10. You ensure that it is melting ice. That's why I say step 1, you say, heat the ice and allow it to start melting. Melting ice. We need to have melting ice. Heat the ice and allow it to start melting. Step 2, insert the bulb into the melting ice and mark the lower fixed point X, which is the level of mercury. Insert the bulb into the melting ice and mark the lower fixed point X, which is the level of mercury. 3, after we have now identified X, we now go to mark the upper fixed point, which is 100 degrees Celsius. Suspend the thermometer above boiling water, not inside boiling water, because this water may not be pure. Or even if it's pure, the pressure where we are is not sea level, it's not standard pressure. So most likely the water will be boiling at a different temperature apart from the 100 degrees Celsius that we expect. So suspend the thermometer, this is point number 3. Suspend the thermometer above boiling water under normal atmospheric pressure and mark the new mercury level Y. Mark the new mercury level Y or B, whichever letter we want to use. This is the upper fixed point. You can add and say this is the upper fixed point. Remember, we are using steam. You can also be asked, explain why during determining of the upper fixed point of a mercury thermometer, steam is preferred and not boiling water. Then you say boiling water may boil at a temperature that's not specifically 100 degrees Celsius due to the effect of impurities or pressure. So after you mark Y, remember now we have the lower fixed point, 0, and upper fixed point, 100 degrees Celsius. We use steam because it's pure. Use, now this is step number 4. Use the grid provided to divide distance XY in 100 equal divisions. Use the grid provided to divide distance XY in 100 equal divisions. Then you conclude. Number 5, conclusion. Each division represents 1 degree Celsius. Each division represents 1 degree Celsius. So that's all for today. Unless there is a question, you are free to leave and prepare for the next lesson. Thank you for attending the lesson.